Hello, today we're talking about catalysis. And there are a couple of key ideas on catalysis that are important to remember. And that is that every time a reaction goes through a catalyzed pathway, it's actually an alternative reaction. We still start with the same reactants and we end with the same products. But the pathway, the number of intermediates, the mechanism is different. The delta G, that would be the difference between the energy of the reactants and the products, is the same for a catalyzed reaction versus the uncatalyzed corresponding reaction. So it's the same. What's different is the delta D double dagger. That's the difference between the reactants and the transition state. So the highest transition state for the catalyzed reaction is lower than the distance to the uncatalyzed transition state. That's your delta G double dagger, also sometimes called the energy of activation. In terms of chemistry, this means that we've changed something about the reaction. So for example, we've been talking about nucleophilic substitution. So to convert a ester to a carboxylic acid, we can imagine that mechanism where water is the nucleophile. But we know that this is not a very effective reaction because the ester is a medium electrophile and water is a weak nucleophile. So this is not a very successful reaction, and we've looked at instead using hydroxide as the nucleophile or the catalyst, because you really got hydroxide in water. The OH minus then is the nucleophile that attacks, but the product is still the carboxylic acid, the methoxide here, which then reacts with water to form methanol and more hydroxide. So we've done a couple of key things here. We're adding a base so that we have a stronger nucleophile. We've changed the number of intermediates and who reacts as the nucleophile, but our starting materials are still water and ester. We still end up with the carboxylic acid, methanol, and we've regenerated the hydroxide. So it wasn't consumed in the reaction. We can also do this with acid-catalyzed. And again, I'm not going through all of the steps in this mechanism. I'm really just looking at key features that help the catalysis. So again, here's our reaction that's very slow or yields very low number of products, which is water plus ester. But if we did instead add the HCl in water with the ester, we've added the acid catalyst. What happens in the first step is that the carbonyl protonates, and we form this electrophile, and this is a strong electrophile compared to the medium electrophile that was over here. Now the water can act as a nucleophile because even though it's kind of a weak nucleophile, we have a very strong electrophile. And eventually, with multiple steps down this pathway, with proton transfers, we end up with the same thing. We end up with the carboxylic acid and the methanol, and we regenerate our proton. It's worth going back and doing these mechanisms for yourself step by step so that you can see all of the proton transfers. But the key idea here is that we have the same starting material, same product, same delta G, but because of an added acid or base, we were able to change the number of intermediates and pathways to improve the reactivity and improve the speed of the reaction.